Good morning, all. Again, we're going to run a new subject today, which is bending moment. It's one of the important and easiest subjects in the course. Let's get started to talk about the bending moment, what it is, how it affects the structural members, and under the bending effects, what's the stress distribution on the section. Okay. Here. Bending moment. In Turkish, eğilme momenti. Okay, here we're going to talk about the case where we have only bending moment on the structural members. Okay. In this case, we will talk about there is only bending moments on the structure. In the real cases, generally, yes, we have some examples where we have only bending moments, but generally the shear effect and the bending moment affects the structural member altogether. Here, the T is shear force. Shear force dm over dx. This is the shear force. So if the m is constant, or we actually, I don't want to write this part. It makes a confusion in your mind. Forget about it. Let me draw directly the sketch about this example. For example, if I have a beam like this, and I have a beam like this, at each side, if I have a moment, this is an example for that. Another example is if I have a beam like this with two cantilevers at each side, such as like this. So here I have a vertical point load, as you can see here, and the main dimensions are here, A total L. By the way, let me draw the moment diagram of the first one. This is the member, and the moment diagram is like this. This is positive, and yeah. For this case, we are gonna see moment diagram like this. minus the maximum moment over here is P times A. P times A. Another example for this case is here. This is the simple beam and with the pin and roller support. I have 2 point loads on the member, which have the equal distances from the supports. For example, here, as you can see, this distance and this one equal to each other. And here, L. These are the P. P, by the way, let me write P so to speak. The moment diagram is like this. So this is the actual single point. You see P times A. This is a positive moment diagram. Okay. These are the simple, basic examples about the where we have only moment. Let's have a new page here. Okay. If we have an arbitrary section such as like this. This is the cross section of a structural member. Okay. So here is the center. So it goes like this. Here, let's say this is a three-dimensional structural member. When we cut the structural member, we are going to see this section. Okay, let's write the X, Y, Z axis on the structural member. Let me change the color. I'm going to use orange to call it this one. I guess. Oh, no. This one. And there will be a vertical component, which is Y. So here, this one is X. This one is the vertical one is Y, and this is Z axis. What we make an assumption in this system, our assumption is all the loads are on the YZ plane. Okay. All the loads are on the plane YZ. YZ is over here, as you can see. This is the YZ plane. Uh, so we call this YZ plane of forces, because but our assumption is all laws are on this plane. That's why it's called plane of forces. YZ as plane of forces. Okay. Here, clear this portion. We have this plane of forces. When this plane of forces coincides with the main structural member here, main structural member, we have a line, which is this one. Change color. This line, which goes all the way from top to bottom. Okay. We have a plane which coincides with the section, this plane. We call this line is line of forces. Okay. Line of forces. This is in Turkish kuvvetler çizgisi. Okay. Line of forces. If this line of forces coincide with one of the main axes of the section, which are X, Y, Z. Let me write this rule. If the line of forces coincides with one of the main axes of the structural member. By the way, what are the main axis members? Let me write here X, Y, Z. Okay. Member. We call this bandwidth, we call this simple bandwidth. This as simple bandwidth, or one axis bandwidth. Bandwidth. Okay. Otherwise, it's called double axis bandwidth. I'm going to explain what it is. Take a look here. What is the line of forces? We assume that all the forces are on this line. Okay, goes all the way along the member, but all the forces are on this line of forces. Okay, so, and this line of forces coincide with the, for example, in this example, y-axis, this is simple bending. For example, another example, let's say my structural member is like this. Okay. So this is, let me see, here is y, here is x, z comes to us, and if we have a loading over here, that means our force, the load, doesn't coincide one of the main axes, x or y. That's why we are gonna have double bending in both of these axes. Okay, we will have a bending around to x and one more around to y. But in the first example here, as you can see, if we have this type of force which is on the line of forces, we are gonna have only one moment which is around the one axis. Okay, we will see this type of problems in the next stage, but we call it like this. Okay, let's have a look at how the bending affects the structural members. Okay, how the bending affects structural. Okay, let me draw a rectangle here. Oh. Okay, this is my structural member. On this member, I have center point and axis. Okay, and we have a bending moment on this member, and here we have changed the color. One vertical line. I'm gonna take into account two different sections on this member. This is A, and this is B, B. Okay. So after the bending, it's gonna have a curved shape. Okay, a curved shape. Let me draw here. I'll try to draw it good. Okay, this is the top edge. This is the bottom edge. Okay. And here, let's see the axis. This is the center. Let's connect these center points to each other. Okay. And we have the bending at this section here. M. Let's draw the A, and B axis or sections on the second sketch. Here we go. let me see. A is over here. B might be over here. But the critical issue over here is A prime is say the B prime. The sections at the initial position were perpendicular to axis. And after the bending, they are still perpendicular to the axis. Okay. The main thing here to make our calculations, the planar sections remain planar after the bending effect. I'm going to write it before that. Let me draw the section here. This is the right. Oh, black. This is the section, and we have axis like this. The dotted line is on this horizontal axis. So we call this axis like okay, neutral axis. I'm going to explain what it is in the next stage. What we said, the sections we assumed at the initial position A and BB, after the bending, they are perpendicular to the axis of the section. So our assumption is planar sections remain planar after bending. Why we do this assumption? In this course, in the subject, actually, we make many assumptions to make our calculations easy. Otherwise, we have to use complex calculations. After we make this assumption, we assume this for our calculations, they're going to be really, really basic. So I'm going to show you the stress distribution. It's like linear triangle. I'm going to show it in the next page. But if we don't do this assumption, it's not easy to define the banding effect on the section by hand calculation. Or we have to do many we have to solve many mathematical equations. This is the basic assumption and helps us to solve the problems. So this works. So we know this assumption is safe at the end of the day. That's why we follow these assumptions and makes our calculation. Now, let's assume that our structural member made of fibers. Okay. Let me show you the fibers. For example, here I have a fiber. One fiber here, second fiber here. Okay, we can go all the way down to the bottom edge. Here, another fiber. Okay. Right. After the bending, what do you see here? As you can see, at the top edge, the fibers around the top edge, fibers will get a shrinkage. Their length will be reduced, as you can see here. Let me draw the numbers change. Yeah. The length of, at the beginning, at initial position, all the fiber lengths are equal to each other. But here, after the bending, at around the top edge, you can see the length of the fiber will be reduced. And inversely, at the bottom edge, the length of the fibers will elongate. Okay. So we have longer fiber at the bottom edge. We have shorter fiber than the initial position, by the way, at the top edge. And at some point, there will be no change on the fiber length. Where is this? This point is the axis of member. So we call this point neutral axis. So as you can see, at the bottom edge, we are gonna have longer fibers. At the top edge, we're gonna have shorter fibers. Longer fibers. And here on the neutral, on this axis, there is no change on the fiber length. So we call this point where there is no change on the fiber length, we call this point as neutral axis. Okay, not neutral axis. I guess you get the point here. What is the fiber change? When we make this band, as you can see at the top edge, we're gonna have shorter fibers, and at the bottom we're gonna have the longer fibers. It's easy to understand when we take a look at this section. So we have longer, we have shorter. The change, the length change in between these 2 points, the longer and the shorter, at some point, there will be no change on the length, fiber length. That point is the neutral axis. Okay, that point is neutral axis. Okay. Now, I'm going to show you the stress distribution on the structural members. I'm going to have a new page here. Okay, let's change the color here, line down. Okay, we have a structural member. Okay. And the stress, the neutral axis here is goes like this. Okay. Now, what we said, what was the strain change? How was the strain change on the fiber length? It's the kind of strain. The length change is the kind of strain. Let me draw this change with the line here. Okay. here we have here. Okay. This one, this one. Okay, now you can see the strain change. The top fibers goes back and they will get shorter, and the bottom goes right, they will get longer. So if we are talking about shortening, this is a negative strain. If we are talking about elongation, it's positive strain because there will be an increase on the member length. Okay, that's why this is positive. This is the strain distribution on the section. Now let's draw the stress distribution here. Again, I'm going to use lines. Let's change the color. I have orange. Okay. Here we go. This is a line and okay, the stress distribution here is like this. At the top, the stress goes into the structural member, stress arrows. At the bottom, stress arrows goes out from the structural member. So if it goes out, it means there is a tension over here. Remember, when we squeeze something, it's compression. When we make straight, this is tension. So here we have stress distribution. So this side is tension side. By the way, this is under the positive moment, which is, I'm going to draw the moment here. This is N. Okay, this is N. Now, to write the equations easily, let's take a point on the structural member. For example, being here, let's have an area here. Area is dA. Okay. Area is dA. dA. So if we follow the dA here, we're going to see stress on here. The distance of the stress to the neutral axis, the blue line here is the, the neutral axis, this is y. So the top distance from neutral axis to top and bottom, let me draw it here. It's like this. C. Okay, C. Now the stress at this point is, which is shown in green, sigma prime. What I'm doing here, by the way, let me explain the problem again. We know the stress distribution. We know by the way, we know the strain distribution. At the top, we have shorter fibers, as you can see, the epsilon minus. At the bottom, we have longer members, and epsilon positive. So if I mark an area on this structural member, the small area is dA. I'd like to find the force on this point to calculate the moment on the section. By the way, okay. If I know the area here, I can draw. By the way, if I know the strain distribution, I can draw the stress distribution, which is shown in orange here. dA is green area on the left side. I can find the stress, which is on this area. Okay, let's say this stress is sigma prime, as I showed with green arrow. Okay, green arrow. Now, by the way, let me write sigma prime. The maximum stress is what? Sigma. And here the required stress is sigma prime. By the way, since we did the assumption, which is planar sections are planar after bending, we can draw the stress distribution like a line, which, as you can see, like this line. Okay. Otherwise, we can't, if we don't do this assumption, we can't draw this line, okay, to present the stress distribution. Okay, we will do this. This is a linear stress distribution. It starts from negative maximum, goes 0, and then goes to positive maximum. The stress change is like a triangle. It's like a triangle. So, how we can calculate the sigma prime if we know the maximum stress? We can use, we know this is a line and distribution is like a triangle. We can use similar triangles. From similar triangles, let me write here. From similar triangles, we can directly write sigma prime over sigma equals y over c. Y, this is the distance of the sigma prime to the neutral axis, and c is the distance of the maximum stress to the neutral axis, as you can see on the sketch. So we can calculate the sigma prime easily. Sigma times y over c. By the way, what is the force on the area dA? Can we define it? What is the dF? dF is basic. You know, the force is, if you know the stress, stress times area. So we have a small area, and on this area, the stress is sigma prime. Let's write the force, sigma prime, stress times area. If we write the moment, the moment of the F around the neutral axis. Okay, we know the force at this level. So if we write the moment, what we are gonna have, dm equals sigma prime. The force is the sigma prime times dA, right? This is the force. This is the force. To define the moment, we need a force and a distance. So let's write the distance. The distance here is y. Because the force is here. Okay, sigma prime times dA. So we are gonna calculate the moment around the neutral axis. Distance to this neutral axis is this y here. That's why I just written here y. Okay, this is y. Let's write here the sigma equation. Sigma prime. Oh, sorry. Sigma times y over c is the sigma prime times y times dA. So here dm is sigma over c times y square dA. This is what? This is the moment which acts on the area dA. It's a small area on the section. Okay, what we are looking for here, actually, we'd like to get the moment which acts on the total section. Okay, we are now talking about a small area. To extend this moment to all the section, what we do, we use the integral. So the moment on the total section, okay, what we're gonna do, we will do integral dm equals, and again this one, this is m, so sigma over c, which is the constant value, take it out, to integral c and y square dA. Okay, here there's an interesting thing, interesting equation here. What is this? If you go back to statics, this is the moment of inertia according to neutral axis. So we are going to use the moment of inertia. That means you have to know to calculate the moment of inertia for the sections. Okay, that we learned in the last term. previous term, the fall term in statics course, you have to know how to calculate moment of inertia of the sections. Okay, that is important. If you can't do that, you can't solve the problem. I guess you understand what I mean. Let's write the equation here again. M is sigma over C times Ix. This is the Ix, by the way. Okay, which is moment of inertia when it classes. If I convert this equation for stress, sigma M times C over Ix. Okay. This is the general stress equation. You can find the stress wherever you want on the section. For example, if you need to calculate, by the way, if we are using here C is the distance from the neutral axis. That means we are going to calculate the stress at this level. For example, if we are going to calculate the sigma prime here at this level, instead of y, we have to put over here y. So this is the maximum. The general equation, which depends on the distance from the neutral axis, sigma equals m over Ix times y. We have to know this equation, guys. You can put here, instead of y, the distance from the neutral axis. If you like to find any stress wherever you want, put there the distance from the neutral axis and then calculate it. But you need to keep your eye on the stress distribution, on the bending moment, where we get the maximum stress, at the top edge and the bottom edge. The edges are important for us. Okay, top and bottom edge. We are gonna get the maximum and the minimum stresses over there. Because when we go inside, we are getting closer to the neutral axis. That's why the stress will get reduced, will get a smaller value. But at the edge, top and bottom edge, it gets the maximum values. Okay, don't forget this one. And you need to know this equation. You need to know this equation. So if generally with this equation, you can calculate the stress wherever you want. What we do generally, we generally calculate the maximum stresses. We deal with the maximum stresses at the top and the bottom edge. So instead of y, we are gonna put c. Okay. Now, oh yes. I will write I'm gonna write a few things about the location of the neutral axis. So it's important to make a decision on it. So the section is in balance condition. Okay, in the section. So the section is in balance. That's okay. And n equals 0. So that means the combination of tension and compression forces on the section is 0. So what are we gonna write? Sigma prime times dA equals 0. This is the force, you know. Sigma prime times dA gives us 0, which is the force, total force, because when I put here integral, that means this is the total force on the section. Now, sigma times y over c times dA equals sigma over c y dA. 0. Here is 0. So to make this equation 0, this portion should be 0. Okay, this is the assumption. So that means the neutral axis goes from the centroid. So neutral axis of the section goes from the centroid. So when you have a section, you are not gonna think about where is the neutral axis. Okay, it's on the centroid of the section. Okay, don't forget this one. This is the reason why I'm explaining this part. So let's make a recap the problem here. Ix is, this is the moment of inertia according to the axis, according to the horizontal, the axis going from the centroid of the section. So y is the distance from the neutral axis so to make calculation regarding the maximum stress, you know where is the location of the maximum stress, top or bottom edge. Okay, the maximum, we are looking for the maximum stress always at the top or bottom edge. M is M. We know moment is coming from the internal forces. I max, Ix actually is this. This is I explain, and we need to take into account the Y max. Y max means the maximum distance from the neutral axis. Okay. So we are going to see the maximum stress at the distance, maximum at the maximum distance. Okay. Yes, we have this one. I have, this is the important equation. This is another form of the previous one. You know, I showed an equation here. Yes, this is another, the same equation, but I try to make everything clear in this part. You have to know this equation. You have to know how to use it. Okay, how to use it. So if the let me see, if the section is symmetrical according to the horizontal axis, yes, we can use this equation. Let me throw you a few different examples. Okay. For example, if I have a T section, okay, or a trapeze section like this, or I have a section with a gap, a rectangular section. There is a circular gap here, or I have a combination of two different sections. For example, I section and U section. Let me draw it. It's possible to see this type of sections in professional life. Yes, this is the IB. So let's draw the location of the neutral axis on these sections. Draw it here. It's gonna be here around here. So see the C1 and C2. This is X. Because why the neutral axis is here? Because the center point is close to the top edge or in the trapeze section, centroid is not at the midpoint. Centroid is close to the bottom edge, as you can see, depending on the section of the geometrical section of this trapeze. It's going to be around here. So C1, C2. Here, change, it's going to be like this. C1, C2. The C1 and the C2 is the distances of top and bottom edge according to the neutral axis. Okay. In this example, here you can see C1, C2. Stress at the top one, let's say 2 point. One, two. Here one, here two. Here one, here two. Okay. Sigma one equals m over ix times, if we are looking for m over ix, it's easy. It's moment over ix. That's okay. If we are looking for the stress at point 1, we need to put the distance that point. It's C1. It's same for the sigma 2. M over Ix is the M over Ix times C2. So here, what we understand, if we don't have a vertical symmetrical section according to the horizontal axis, if we are looking for the stresses at the top and bottom, yes, you can do this calculation. If you are looking for the maximum stress, you can calculate sigma 1 and sigma 2 and get the maximum one from there. Or basically, the maximum stress is gonna occur at the maximum distance. Basically, this portion is distance. If I put here a higher number here, I'm gonna get a higher stress. So if you put here directly the maximum stress, maximum distance, you're gonna get the maximum stress. This is a general logic. Okay. We have two types of problems in this subject. The problems are the check of the section. We check the sections. Okay. We check the section. If they work under the given moment or not. This is one case. Right here. First case, we know the section. We know the material. We know the moment. Okay. So what we do, we know section. Section means all the dimensions of section. So we know the moment of inertia. We know the material. That means we know the allowable stress. We know the moment which occurs the stress on the section. So according to the given data, according to what we know, we can calculate the stress. So at the end of the day, we have to check the stress, if it's less than the allowable stress or not. So calculated sigma max, sigma allowable. This comes from the material, okay. Another question type here is this one. We know the section again. We know the material. We know the section and material. What we can do, we can calculate the M capacity. We can calculate the moment carrying capacity of the sections. And second type of problems, what we do, we design the sections. Okay. So, yes. What we do, we assume that the sigma maximum equals to sigma allowable. Okay, sigma allowable, as usual. When we design a section, if we don't know anything about the dimensions of the section, we assume that the stress level is allowable stress. So sigma max equals sigma allowable. And then what was our equation? M over I x times y max. Okay. If we take down to this y max like this, M over Ix times y max. What is this? Can you remember what this is? This is the elastic modulus of the section. This is Yx. You don't have to do it like this, but if you want, you can do. Wx is elastic. Section. Remember, it was in centimeter cube. So to make a section design, here we don't know the dimensions of the section. Okay, don't forget this one. We don't know. We are trying to get design means to determine the dimensions of the section. We don't know it at the moment. So this is Wx. So we can calculate the Wx. Wx equals M over sigma allowable. So this is the required. This is the required Wx for this load value. So if we know the elastic modulus like this, we can select a section which has this elastic modulus or which has a higher elastic modulus than this one. So what we can do, if we have a rectangular section, you know, oh, sorry. Here rectangular section. This is H. This is H. This is B. Half of it is H over 2. Remember how we calculate the Wx, the moment of inertia over the distance of top, H over 2. So which is this is for rectangular sections easily. Yes, in design problems, we try to determine the size of the dimensions or of the sections. Okay. And the last subject, by the way, I'm sorry, I missed the break. Let's have a break, and then I'm gonna explain the last subject. Then I'm gonna solve a few problems regarding the bending effects. It's 10:25 according to my clock. We are gonna be here 10:55. Okay. Okay, guys. See you. Okay, next. Okay, I'm gonna talk about the double axis bending now. Okay, remember, if the line of forces does not coincide with the major axis of the structural member, there will be double axis bending. Okay, let me explain this on sketch. Here we have an inclined surface like this. And let's say this is a rectangular purlin on the roof. So here, this is the center of the this is the x-axis, y-axis. So here we have this is the line of forces. As you can see, it doesn't coincide with one of the major axes. These are the, this one and this one, major axis of the structural member. So in this case, we have double axis bending. Double axis bending. We can think about the bending like it's a combination of two simple bendings. Okay, one is around x-axis, the other one is around the y-axis. Double axis bending is this actually. We are gonna have two different bending. One is around X, one is around Y. So we combine both of them and get the result. That's it. Let's draw a section to define it. Okay, this is the rectangular section, and these are the axes. This is the X, and this is the Y. Okay. X, Y. So here we have a bending is around x-axis, mx, and the other one is around the y-axis, my. Okay, we have two different axes. So how can we calculate the stress for this case? Firstly, we think about the x-axis, mx over ix times y. By the way, if we are looking for the stress at this point, here is x, here is y. Okay. My, iy times x. We have to use this combination. As you can see here, we use plus and minus. We do both of them and consider which takes the maximum value. In the examples, we are going to see this. Now, actually, we have just completed the subject. I'm going to solve a few examples. Let's get started. The first example. First one is we have a rectangular section, and its dimensions are, this is B, this is H equals double B. Okay, so mx on the section is 2.7 ton meter. Allowable stress of the section is allowable. That means we know the material is 85 kilogram per centimeter square. According to this given data, please calculate the dimensions of the section. What is B and what is H? Okay. What is B? What is H? We are going to do an design issue. Remember what we do. Sigma is m over ix times ix times y max, right? If we take this down to here, we will see m over ix over y max. This is the, you know, Wx, which is required. So we are going to calculate this part. required Wx, then we will decide dimensions. So in these type of design questions, we take into account allowable stress as the maximum stress. So, sigma allowable equals m over Wx, basically. So from here, if we take out the Wx, which is we are looking for, is m over sigma allowable. Now, the other part is basic. We are not doing rocket science here. It's easy. You can do it. Wx equals m. M is what? 2.7 ton meter. 2.7 ton meter. So allowable stress over here is in kilogram centimeter. Let's convert the total ton meter to kilogram centimeter. 2.7 times 10 power 5. This is for the unit conversion over allowable stress, which is 85. Now we have this one. This is the required section elastic modulus. Okay. Mukavemet momentu. Now we can write the equation for it. Wx is for the rectangular sections, as you know. So let's write the equation. B times H equals double B, and square over 6 equals this one. Now, what we have, 4b cubed over 6. Here, there is only one unknown, as you can see, which is b. So from here, you can calculate b like and h. Yes, these are. As you can see, b is 16.83. Okay, in real life, we don't use these type of numbers. Instead, we can write b is 17 centimeter, h is 34 centimeter. Okay, if you do this, that's okay. In real life, we round up the numbers. Okay, basically, we round up. Okay, this is the first question. Any questions so far? No, I think yes. The second question here is, we have a T section. We have a T section. This is the second question. Yes. Okay. For this section, the moment is 0.30 meter. Sigma allowable is 85 kilogram per square. The question is here. What is the sigma top? What is the sigma bottom? Sigma top means the stress at this point, and the stress sigma top is here. Sigma bottom is here. Okay. These are the questions. By the way, I'm gonna clear this part and write again the dimensions of the section. 16 centimeter here. Here is the 4, and here is 18 centimeter. This web thickness is 4, and the flange width, left and right side, 6 centimeter, 6 centimeter. Okay. Yes. Now, what we are gonna do? The moment on the section is 0.30 meter. Allowable stress is as seen on the screen. Top and bottom stresses. In this question, remember, we need to know where the neutral axis is. Okay. Where is the location of neutral axis? The location of the neutral axis is the horizontal axis, which goes from the centroid. So we need to find the centroid. Okay, we need to find the centroid, where it is. It's, I guess, it's basic. You can do it easily. You know how to calculate centroid from the statics course, but I'm gonna do it now again. Let's consider we have two rectangular sections at the top and the bottom here, over here. Now, we are gonna calculate the distance from the bottom edge. So let's write the equation YG. Okay, the area, remember, area of the first rectangle is 16 times 4 times the center point distance to bottom edge. Center point distance is here, right? 2 plus 18. Totally, it's 20. I guess you know this one. This is a kind of recap for you. Okay. This is for the first rectangle plus the bottom rectangle area is 4 times 18 times the center point distance to bottom. Center point is here at the midpoint of here. The total is 18. The half of this total length is 9. That's right here, 9. Okay. Over the total area. Total area is 16 times 4 plus 18 times 4. This gives us the location of the neutral axis, which is so let's show that line on the, here we go. Okay. This is, we have just calculated this part. This is the 14.18 centimeter. Can we calculate the distance above? Yes. The total distance, the total height of the section is 22, according to given dimensions on the sketch. So 22 minus 14.18, which gives us 7.82. Okay. So we know this line is the neutral axis, and this point is the centroid of the section. Okay. Now we know the location of the centroid. What we will do, we have to calculate the moment of inertia. Moment of inertia. Let's do it. Ix. I assume that you know the calculation of the moment of inertia well. I have to do this assumption because we can't go back to statics course. You have to know how to calculate it. Basically, you may know the rules regarding the bending moments, yes. But if you can't calculate the moment of inertia somehow, you can't solve the problem. It's not about what you know about the bending moment. It's about what you don't know about the previous of this course, statics. That's why please take a look at these issues. If you keep all these recap works to the last night before the exam, 100% you can't learn everything. Please try to make some examples before the exam day. So I hope you are gonna do it easily. Yes, Ix. Now let's do it for the first rectangle. First rectangle is here. This one is 60. By the way, what is it? Yes, 16 times 12. Now, I'll just calculate the moment of inertia according to this local axis. Now, we're going to transfer it, shift it to the global axis, which is the orange one. Plus, how we do this, after we calculate this rectangle's moment of inertia, plus we add area times distance square. Area is 16 times 4. What is the distance? Okay, we're gonna do it. The total distance from here, top to orange line is 7.82 minus 2, because half of this section is, this is 2, minus it, it's 5.82 square, plus, let's have a look at the second rectangle at the bottom. 4 times 18 cube over plus, this is the moment of inertia according to this point. Let's shift it to the global axis. Area times distance square. Area is 18 times 4 times. What is the distance? What is the distance? It's easy. The total distance till here is this one, 14.18. But we know this portion is 9 minus 9 square. That gives me the distance here. between 2 points. So if we solve this equation, we will see what equals. The result is here. This is the moment of inertia. Okay, let's write the sigma top. Right? Let me remind you, sigma top is here. Sigma bottom stress at this point. Okay, sigma top. Moment 0.30 times 10 power 5. This is for the unit conversion. Over moment of inertia and the distance to the top edge, okay, which is 7.82. Let's write the sigma bottom. This portion is same. The only thing which is different, the distance part. Distance part is distance to the bottom edge, which is. So if we make these calculations, here I have here. Okay, here we have the stress at the top and the bottom. Question here, which one is compression stress, which one is tension stress? Basically, let's have a look at the moment given in the question. It's a positive moment. If we are talking about the positive moment, tension is always at the bottom, compression is always at the top. Inversely, if we have a negative moment, tension is at the top, compression is at the bottom. So let me write for the top, this is compression. And for the bottom, this is tension. So that's all for this question. Let me have a look. This question. I'm looking for any question which is good for you. Yes. We have another question. Actually, the questions are really basic, as you can see. For example, in this question, what we should do, we calculated top and bottom stresses. We should show all the stresses are less than allowable stress. Okay, the allowable stress here is 85. This is less than 85, as you can see, and this one is less than 85. So this section works for us. Okay, this is good. If one of these stresses are greater than 85, that means this section doesn't work. So it fails. We have to increase the dimension of the sections. Okay, Okay, so the question here, line, here, the third question is, we have a wall like this. Let me draw it. So I'm gonna draw it again. Okay, this is much better. Here you're gonna see corner. This is a wall. Dimensions of the wall is here 60 centimeter. Here we have 130 centimeter. The height of the wall is 3 meters. So 3 meters or 300 centimeters, whatever. So we have two different loads on this number. One is just a second, which acts in this direction, and the other one acts in this direction. So just a second. This one is 2 ton. This one is 3 ton. Okay. So the question is, please calculate the stresses at the bottom level. At the bottom level. This is the ground. Okay. This is the ground. Please calculate the stresses at the bottom. Okay, let's do it. Here, basically, this is a structural system like this. Vertical cantilever. Okay, vertical cantilever. So, depending on this, we have this axis system and this axis system. So, what we have 3 ton, and here we have 2 ton. Today I have a fixed base. This is a vertical cantilever. Okay, this is the question. So, the height of the member is 3 meters, remember. So what we have, if we say one direction is X, one direction is Y, let's say this is X. Oh, I'm sorry, let me change the color. That's gonna be better. Here you can see the x-axis at the bottom. This is the y-axis. So Let me draw the section over here again. Section is like this. And here, this one, here, this one, centimeter. By the way, in this direction, we have 2 tones. In this direction, we have 3 tones. Okay, 3 tones. So let's calculate the moments first. Moments here. Choose x, x, y, y. The mx here is 3 ton, 3 times. The height is, because we are just calculating the moments at the base level, so 3 tons times the height of the structural system or height of the cantilever, 3 equals 9 ton meter. My is 2 times 3 equals 6 ton meter. Okay, 6 ton meter. Now, what we are gonna do, we have to calculate the Ix and Iy. Ix equals this one and this one, centimeter 4. Iy equals, yes, this one times 3 cubed over 12 equals. It's again 2,340,000 centimeter 4. Okay. Under these 2 loadings, we have double axis bending, as you can see in the system. So we are going to use the double axis bending equation. Let's write the equation here, m1, m2. We are going to calculate both of them. The moment, let's convert it to kilogram centimeter with power 5 here. This is the moment of inertia. What we need the distance, maximum distance, which is half of the 130, which is this one, because we are looking for the stress here. And plus minus, the number plus and minus, we have 6 ton meter and power 5 kilogram centimeter, 2 million, again, this one, times half of this total distance, which is 30. So if we calculate sigma 1 and sigma 2, we are gonna see 2 numbers here. Sigma 1, let's say, is sigma 2 okay. Now what we do here, you know, this force occurs a bending like this. Let me draw it. This is the mx moment. Okay. This is the my moment. So as you can see here, at this portion, I'm gonna have, by the way, I will draw the, let's change the colors. Color, blue. Blue shows the compression. See, yellow shows the tension. Okay. I'm gonna draw all these tension and compression sides. Now, under mx, what we will see? Let's go compression. Under mx, it's the moment arrow is like this. The arrow side, the compression side. Okay. For this side, we have compression. For this side, we have compression. Okay. And so, and we have tension here for mx. Let's look at the my. My starts from here, goes to right hand side. The arrow side is the compression side. So we have compression here. We have compression here. And let's start side. At the left hand side, we have tension. We have tension, as you can see. So if you look at the corners and the colors, we have, let me change color. We have double blue here, double yellow here. So in double axis behavior. So we have, if we have double color at these corners, we have the maximum stresses at these corners. So we can say this is the compression. What I'm gonna have, I will have, let me write, totally compression stress here. And I'm gonna have totally tension stress here. Okay. The minimum is where we have two different colors. Okay. Two different colors. This side is double compression. This side is double tension. Because since we have tension and compression, these points, they reduce the magnitude of moment. That's why we are gonna have 2.37 here, 2.37 here. These are the location of the stresses. Okay, you can calculate the maximum and the minimum stresses, but you need to understand what we have, which one is the maximum stress, where is the location of the maximum stress and minimum stress. As you can see here, I use the color method, or if you can do it, I have the colors here to do that. Instead, you can do, for example, plus, and you can use some signs and star. You can follow this method by yourself while you are doing. So we have just completed the moment case. Okay, moment case. Last week in this term, we are gonna do more applications all about the all subjects. So before that week, I suggest you to take a look at these subjects by yourself, and I suggest you ready to come class at the application week, because application is the last week. If you have any trouble, anything about the problems, we can discuss all these issues. So that's all for today. Thank you for your attendance. Take care of yourself. See you guys. Bye-bye.